Literally a block that is showing signs of life on this thing. This is a stepping stone to the rest of space. Hello and welcome to the RedMars Podcast. Welcome back to another episode. I know it's been some time, and that's because I've had some things going on. I was actually for work traveling up in Washington not too long ago, pretty much all last week and part of the weekend, and I am actually in the transition of roles at my job, switching from one team to another, and just been getting some things sorted out. With that, I've decided that this episode we're going to talk about something known as ISRU, or In-Situ Resource Utilization. Reason I've chosen this topic for this episode is because there's so many things going on right now, specifically with the moon, and trying to create a permanent presence in space, whether that be the moon or beyond to Mars or whatnot. And there's been some discoveries lately about other planets, one in particular that's 120 light years away. Don't recall the name of it anymore, but they're saying that there is showing signs of life on this planet, mostly due to the chemical makeup that they're finding that tends to be, to our knowledge at least, only produced by living organisms. They expect it to be a very lively oceanic planet. Think of oceans everywhere, marine life and all that, and super cool. And that whole topic got me thinking about ISRU, or In-Situ Resource Utilization, which really is the study or the ability to use what you have at your disposal in front of you to create resources or materials or create products from it. Think of like manufacturing. You're in the desert, you have what you have in front of you, make something from that. And while at first thought you might think there's not really much you can do with a bunch of sand, really there's a ton you can do. It has all the building blocks you may actually need to make something. And so that's what we're going to talk about today. So we're going to start off talking about the moon. The same practices can be used all over the place. You'll see some of the stuff I have up here today for those that are watching. You'll see some images from lunar surface, from Mars, and some of these different technologies. And then I have a slide that I want to share that I did when I was in my master's program. I did a Masters of Space Systems at the Florida Institute of Technology. And with that came a capstone project. And we did a Lunar Prospecting Mission. I led the effort. And we did this whole project that did everything from choosing a launch vehicle, the astrodynamics of everything, propulsion units, guidance, navigation, control algorithms, and actuators, everything you needed to do for this entire mission, down to the mission profile, to landing on it, designing a lander, designing lunar rovers, the communications that's going to be there, so all those systems and everything. We didn't go super in detail, but we went down to the level of detail of an architectural diagram or block diagram, calling out the different technologies we'd used, how they'd communicate and everything like that. And then we even broke down how those prospecting robots would actually make use of lunar regolith to determine what the makeup is of the soil, how they can use it, and how they can produce, say, different raw materials from that can be the building blocks for future missions or used there for, say, fuel and life support systems and all that. So we're going to dive right into it. So let's start with this first one here. So using space-based resources for deep space exploration. So this is one of the main reasons we are going back to the moon. The moon's going to be kind of the central hub for really all countries of the world as a starting point to have access to the rest of space. And the reason being is it is a very rich soil with ice crystals in there as well that you can be used to harvest water. And there's several processes you can do this to harvest water from that lunar regolith. And one can just be heating it up where the ice crystals are. And you have to get it to temperature, say like 150 to 200 degrees Celsius plus. But what this does is melt those ice crystals. Then you can harvest those ice crystals as, I guess it would sublimate, and then you get the gas. You collect the gas, it condenses, then you get the water from it. And then you can break apart that water and get your hydrogen and oxygen, which then gives you your rocket fuel and oxidizer or breathable air as well. And you can use this for the, I guess, ecosystems if there's going to be environments or bases built on the moon, or rocket fuel, or both, or whatnot. So lots of use cases there. Now, another process you can do is something known as a hydrogen reduction process. And this is very helpful for maybe where you don't have ice crystals, but you can take it out of the soil itself from, say, the ilmenite. And ilmenite is a iron titanium oxide material that makes up part of the lunar regolith. Now, what you can do to this is put it through this hydrogen reduction process. Pretty much you melt it, make it super, super hot, and flow through hydrogen. And the hydrogen reacts with the iron titanium oxide and breaks it apart into several elements. And what you're left with is a metallic iron material. So pretty much you have your iron, titanium, I guess it's titanium oxide you'd be left with, and then you have water, H2O. And that's your products from that reaction. So you would melt it, and then you can extract out your iron, titanium, and whatnot. And you got really good building blocks and materials for building spacecraft and different types of, say, electronics and that on the lunar surface, which allows you to build and stay on the moon for a longer period of time because you don't need to go and ship these materials up from Earth. And that's an expensive process. We've talked about this several times before. I believe it used to be about $10,000 a pound or kilogram. I don't recall which one it was. But it is expensive to get something off Earth, especially super dense materials like iron and water. And those are essential building blocks. So let's look at this here. So when NASA returns to the moon with the Artemis program, they plan to put in place sustainable infrastructure that will allow us to explore and study more of the moon than ever before. Right, you're not limited to durations on the moon now as much as you were previously because you only had a limited amount of supplies. If you don't have to bring as much oxygen and water with you because you can produce that where you're going, well, you can stay a lot longer. Like imagine you were going on a vacation, say, to Mexico, but they have no water or breathable air. You had to bring all that with you. It'd be a pretty short trip. So same idea goes here, just a bit more, I guess, larger consequences if you don't pack accordingly. All right, so we need a better understanding of what the resources are, or what resources are accessible on the moon today to support the exploration and what technologies work to process those resources. This is going to lead us into another conversation of what Blue Origin actually has done, which is super fascinating. There was nowhere near enough, I guess, publicity around this. This happened back in 2021. We'll talk about it in a moment. But it was really groundbreaking and is still groundbreaking on how they can use these resources to create something super useful. All right, so demonstrating this on the moon will help us get ready for missions farther into the solar system, including Mars. And that's what we've been saying. This is a stepping stone to the rest of space, including Mars. So Elon Musk saying, we must go to Mars, we must go to Mars. Sure, but you got to step through the moon first, unless you want to take that really large leap, but there's a lot more risk involved. If you can demonstrate it on the moon somewhere a bit closer, you can actually go from the moon to Mars, which might be a bit more feasible. You can build bigger spacecraft and that without the need to get through an atmosphere like we do here on Earth. Now, you would still have to get through the atmosphere to get to the moon, but the moon can be kind of like your Wawa or gas station, refuel station. We have Wawas down here in Florida, so Wawa's a good place. But anyways, it's like your refueling station to get you where you need to go, which means you don't need to bring as much fuel with you to get off the Earth. Again, cost savings, and allows you a bit more flexibility in the mission. All right. Let's see what else NASA had to say. So to live and work in deep space for months or years may mean crew members have less immediate access to the life-sustaining elements and critical supplies readily available here on Earth. That's what we've been saying. So NASA will send cargo, experiments, and other supplies to the Gateway in lunar orbit to support exploration on and around the moon. However, the farther humans go into space, the more important it'll be to generate products with local materials and practice called In-Situ Resource Utilization, ISRU. Now, taking a step back here, we mentioned Gateway in lunar orbit. So what exactly are they talking about here? So if you haven't been following along with the Artemis missions and what that mission profile looks like, there's something called Gateway. And this is a joint effort between space programs around the world. I think this one specifically was between the US and Canada and possibly Europe as well. And they are building a gateway, more or less another stepping stone that'll be a space station more or less in orbit around the moon. And that's kind of your first point before you make your final descent down to the lunar surface. So you'll go into usually a parking orbit on Earth once you launch from your launch vehicle. You'll sit in a parking orbit, you'll do your checkouts and everything, and prepare for that TLI, or translunar injection burn. And then you'll do your big burn, that's your major burn that gets you out of the gravitational pull of the Earth, and on that trajectory to go and capture a lunar gravitational, or the lunar sphere of influence. And then once you get into that, that is where you're going to do more or less a retrograde burn or a slowdown burn, which gets you into a more approachable speed. You'll do your rendezvous guidance, and you'll rendezvous with this Gateway space station. Once you're on Gateway, typically you'll take a break, you'll go in, stretch your legs a bit, it's been a long journey, and then you'll prepare for your descent down to the lunar surface. Once you're on the lunar surface, that is where you'll make your landing at your point of interest, depending on what the mission may be, and you'll perform what you need to on the lunar surface. This is, again, before we have those lunar bases. Once you have a lunar base, you might be going down for an extended period of time on the lunar surface, but until then, there'll be shorter trips to the lunar surface to do some sort of prospecting, proof of concept type of exercise before returning to Gateway and making your journey back to Earth. All right. We're not going to dive too much into the depths of what NASA's got going on here, but more or less what these images are showing is, well, the first one here is kind of interesting. It's looks like farming equipment, but it's a cultivation of that lunar regolith and bringing it over to a extraction device or a processing unit where they're going to extract out those different elements and the building blocks for, say, life support, rocket fuel, and whatnot. And this other image here that I am looking at is a picture of more or less the same thing, but a storage location that has a bunch of cylinders that most likely has the different hydrogen, oxygen, and possibly liquid water stored in there as well. For liquid water, you'll need some sort of environmental control or ecosystem that allows you to keep it at a temperature that allows it to stay liquid, or you can do through pressure and whatnot. But that's more or less the gist of what's going on here. As you scroll through this page, you'll see other current missions that are or have taken place or going to take place for prospecting the lunar surface, including in big craters. One of the major craters to note is the Shackleton crater near the South Pole, and there's been thoughts to have lots of frozen water under the soil there as well. Now, ISRU investments. NASA is making long-term investment to advance ISRU technology in multiple areas, including particular focus on regolith-based volatile resource acquisition and processing. So that's what we've been talking about, getting those main resources from the soil and extracting them. Regolith-based in-space manufacturing and construction. This is an interesting one. So not only creating those different resources from the soil or extracting them, but creating building blocks, literally a block maybe of lunar soil as cement or the building block for structures. So think of the 3D printing process, but of lunar soil, or robots that go and build bricks on the surface of the moon so that when people get back there, they can use them to build things, or you even have robots that come in a later mission and use those to build structures so that when we arrive, everything's more or less ready to go and turnkey. Obviously, there'll be a bit more to it, but the closer we can get to that, the safer it'll be for humans once we arrive. And then finally, Mars atmosphere-based resource acquisition and processing. So this is being able to study the Mars atmosphere, what thin amount is there. And I know there's been some talk about how do you create a more livable atmosphere on Mars. Some people have said nuke Mars and create a nuclear winter there to trap all the gases and really create an atmosphere that over time would then be livable or habitable by humans and other life forms. So many thoughts out there, all interesting. But now let's take a look at something that, actually, before we get into Blue Origin's technology, and it's known as Blue Alchemist, since we already mentioned ilmenite, let's talk a little bit about the benefits of ilmenite. So this is very quick. We're not going to go through and read the actual paper on this or this publication, but I guess we'll say this was done by Joaquin Ruiz of Arizona University, Tucson, Arizona, United States. And this was the talk of the benefication of lunar ilmenite. So this is why it's so important. So ilmenite, or FeTiO3, that's that iron titanium oxide, is considered one of the leading candidates for production of oxygen because it can be reduced with a reasonable amount of energy and is an abundant mineral in the lunar regolith and many mare basalts. So, yes, energy is always an issue. The cost to actually extract these things. How do you get the energy to do it? So there's thoughts of using solar energy, bringing energy with you, whether that be nuclear reactors, electric energy batteries, whatnot. or chemical reactions as well. How do you actually do this process? We said molten soil. How are you actually going to melt that soil? Well, there has been demonstrations in the desert here on Earth using large focusing lenses to focus the solar energy and actually melt the sand of the desert into glass. So it creates a molten glass, and then as it dries, it solidifies, and then you have the leftover element there. So the same idea could be used on the moon, and you have a lot less atmosphere for that solar energy to penetrate, which makes it possibly a more viable option. So this paper, as I have not read through all of it, it does seem like it would be a good read for those that are interested in this topic. For today's purposes, we're just going to kind of skim over this real quick, but just wanted to mention that. And then one of the other processes, this is from a slide deck that I used in my master's program, talking about water production for in situ. So this is using that hydrogen reduction for oxygen extraction. So the idea here was these lunar autonomous robots designed to extract lunar regolith for the hydrogen reduction process. They would collect the lunar regolith at a point of interest, and this regolith is then placed in a heating chamber in preparation for the next step. That next step is the reduction process. So hydrogen gas is pumped through heated lunar regolith, reacting with the metal oxides, producing water vapor and excess hydrogen gas. Lunar dust is also a byproduct in this process and will need to be separated. So they can do this through a centrifugal kind of spinning process and separate the dust particles out and the other heavier elements, leaving the lighter ones more in the center that you can kind of suck out of there. So that brings us to the separation process. So during the separation stage of this oxygen extraction process, the lunar dust will be separated from the rest of the gases by a vortex chamber, forcing the dust to separate from the rest of the gas, allowing the gases to flow through to the next chamber. This brings us to that chilling chamber that we mentioned where you'd condense it. So the chilling chamber, or the chilling process, is what will trap the water vapor and distill it into liquid water. The liquid water is what will be the interest and purpose of our mission. This was the mission that we did for my Masters Capstone, and that's what the whole process was here. And then you go through the analysis. So the analysis is the final step of the process, where a spectral analyzer, which pretty much you're looking at the chemical makeup of what you've just extracted, and it'll verify the produced water from the hydrogen reduction process. Once the analysis is complete, the liquid water will be ejected back into the lunar surface. So we're not actually planning on bringing anything back on this mission. We just want to go and sample soil, different parts of the lunar surface, and determine what the makeup is and how efficient our process is actually working. There is a note here that an added step of electrolysis could be added to separate the oxygen and hydrogen to reuse the hydrogen for various purposes and storing the oxygen for future missions. So that would allow you to go that one more step where you have your water and separate the hydrogen and oxygen, giving you more or less rocket fuel and 100% oxygen gas. And that oxygen could be used as an oxidizer for rocket fuel, or the oxygen could be used as breathable air for humans. All right, now while we're on this, I can show you a few more slides here. These were some of the CAD drawings that I put together of the prospecting robots, not super in detail, but wanted to give more or less just a general idea of what they look like and whatnot. Here was the lunar lander. We had the ramps double as a solar array, and how this would work is, well, you can see there's other arrays up top here, but after the robots would come out of their kind of holding cells, these legs would stand up and be vertical, and since we're at the South Pole, you almost have that 90-degree incident angle, so that's why we had them like this. The inside here would not really be too useful, but as you'd stand it up, you get this large panel that would allow you to do it, and the other side just kind of looked cool. Anyways, this was kind of the main breakdown of it. The dry mass of this lander was 10,354.89 kilograms, and it was the single lander that contained 8 autonomous robots. The fuel tanks were made of a carbon fiber composite with an inner radius of 57 centimeters, and this was all calculated based on the fuel needed for our burns for our mission profile. And I believe, here we go, this was kind of the full breakdown of what everything looked like. And the mission profile, I can find it here. Should be a bit farther down. Let's see. Here we go. Here's the mission profiles and the timeline. So we were using a Falcon Heavy at this time. It would send our spacecraft up, we would separate and drop down and land on the moon. So that you'd have low Earth orbit, high Earth orbit, high lunar orbit, and low lunar orbit, and then you would do your placement down. And this was a throwaway mission, so the lunar lander would more or less rest of its life on the lunar surface until the end of time, or other purposes came from it. But here was our communication subsystem block diagram. So went pretty good in detail, but not down to the actual components themselves. But we talked through, S-band components and that. So we had our ground, everything really planned out here pretty well. There's a lot of cool information in this, but we won't go too into detail. So before we go on for too long, let's move over to Blue Alchemist. So this is the super cool breakthrough that Blue Origin came up and was able to do that didn't really, in my opinion, get enough attention that it should have, especially for what they managed to do. So, especially in terms of in-situ resource utilization. So this was published back in, it says, February 10th, 2023. Blue's been doing this since 2021. And what they do is they are making solar cells, as you see in this image. And for those that are listening, it's a small circular kind of wafer disc, if you could, if that makes sense. And it is a solar cell. So it has that kind of bluish purple tinge to it. And of course, they have their signature feather imprinted on there as well. But I'll read the first little bit here for everyone that's listening here. So since 2021, Blue Origin has been making solar cells and transmission wire from regolith simulants. So regolith simulant is as close as you can get to lunar soil without having lunar soil. So from the Apollo missions and other missions that have gone to the moon, prospecting missions that can tell us what the lunar soil is made out of, we've been able to make simulants, or soil that represents that here on Earth, for us to test with and try out these different experiments. So Blue Origin has been able to use these regolith simulants to make solar cells and transmission wire. So to make long-term presence on the moon viable, we need abundant electrical power. We can make power systems on the moon directly from material that exists everywhere on the surface without special substances brought from Earth. We have pioneered the technology and demonstrated all the steps. Our approach, Blue Alchemist, can scale indefinitely, eliminating power as a constraint anywhere on the moon. We start by making regolith simulants that are chemically and mineralogically equivalent to lunar regolith, accounting for representative lunar variability in grain size and bulk chemistry. This ensures our starting material is as realistic as possible and not just a mixture of lunar relevant oxides. We have developed and qualified an efficient, scalable, and contactless process for melting and moving molten regolith that is robust to natural variations on regolith properties of the moon. Using regolith simulants, our reactor produces iron, silicon, and aluminum through molten regolith electrolysis, in which an electrical current separates those elements from the oxygen to which they are bound. Oxygen for propulsion and life support is a byproduct. It's a pretty good byproduct if you ask me. For those that are listening, there's an image here showing the molten regolith coming from, or flowing from top to bottom in this gold glowing form. Looks like liquid. And then we move to the next one here, which says our proprietary transport subsystem moves and separates molten materials at temperatures above 1,600 degrees Celsius in a controlled and power-efficient manner while withstanding the high temperatures, corrosive environment. The next image shows what looks like a boiling liquid. So the molten regolith electrolysis extracts iron, then silicon, and finally aluminum by passing a current through the molten regolith. The rising oxygen bubbles, those are the bubbles that are being shown in the image here, in one of our reactors shows metals and metalloids being separated from oxygen. Our reactor geometry, metal extraction approach, and material selection will enable sustainable lunar operations. Our process purifies silicon to more than 99.999%. This level of purity is required to make efficient solar cells. While typical silicon purification methods on Earth use large amounts of toxic explosive material or chemicals, our processes uses just sunlight and the silicon from our reactor. So it sounds like they're using a similar approach to what I mentioned that other gentleman used in the desert here in the United States to melt melt just sand into glass, and he was actually using it to 3D print different objects out of the sand, which is super cool. But yeah, same idea, I guess, here, and without the use of any toxic or explosive chemicals that could harm the environment. Now, obviously, the lunar environment is much different than the Earth environment in terms of living organisms and that, but we still should not be polluting anything. And if we can do this process off Earth, that means we probably don't need to do it as much on Earth, which then helps keep these toxic chemicals and that out of our environment where we live. Closing out here, our novel process fabricates solar cells, including cover glass, using only products from our reactor. These long-lived cells resist degradation caused by radiation on the moon. Here we show silicon melting as well as a thin layer deposition that makes solar cells. Super cool. So I'm not going to read through the rest of this. If other people are interested, feel free. This is on their website. You can just go and search anywhere on Google or whatever search engine you use for blue Alchemist technology, and you should be able to find this. The very last part is a blue rendered image that shows what the implementation of blue Alchemist would look like. It is super cool and flashy and an all blue style, very attractive looking image. And yeah, looks very cool. So very excited to see how this makes its way to the moon and eventually on Mars. And that's, as we mentioned, it's not just all about the moon, but for now, the moon is our proving ground before we go to Mars so that we can really say, hey, we're making this happen. So very exciting. And with that, that is really all I wanted to talk about today. So I hope everybody enjoyed this talk, and if you did, definitely feel free to leave some comments in here. Let me know what you think about this. If you think there's other methods that could be done, better methods, or maybe you disagree with some of the work that's being done by some of these companies, I'd really like to hear your thoughts on this, or maybe other areas that you could try this out. So interested to hear what you have to say and any feedback, of course. And as always, there's other ways you can try this out at home. You can actually buy lunar regolith simulant online. Companies like Stem Cell, I think it's called Stem Cell Lab or Stem Cell Research. If you do a search online for lunar regolith simulant, you can buy some yourself. They come in little vials about this big, and I think they're range anywhere from $5 to $10. Maybe gone up a little bit since I last purchased them. I bought some about 5 or so years ago, maybe even longer now, actually, I think about it. Anyways, it's been a while. Great stuff to play with. You can see how maybe you can do some experiments on it and separate some materials yourself. You don't necessarily have to melt it. There are other ways to extract things, hint, hint. Have some fun with it. See what you can do. And with that, stay curious, everyone. Keep looking up. And until the next one, everybody take care and enjoy your Easter weekend for those that celebrate Easter. Take care, everyone.